So welcome to the lecture on geotechnical engineering with respect to the previous year questions. The first topic would be the properties of the soil. Okay, so let's do a few questions which were asked in the initial part of soil mechanics. So which deals with the definitions, okay, such as a void ratio and its corresponding things like porosity, degree of saturation, and combined with these relations. Okay, so we'll look into the few questions in this chapter. Okay, fine. The first question would be the it was asked in GATE 1991. For sand of uniform spherical shaped particle, the void ratio in the loosest and the densest state are dash. So it is already mentioned that the soil particle is a spherical in shape. The soil particle is a spherical in shape. So we have a standard notation that the spherical shaped soil particle, if it is arranged in a cubical array pattern, so in such a way, so similar to the numbers placed in an array. So along a row, along a column in a well formatted manner. So whereas the other form is the other one is a diagonal packing. So if the soil particles are placed along the diagonal with respect to the adjacent particle, for example, this is a row of soil grain. So the particles were placed along the diagonal, along its diagonal, right? Okay. So whereas in the cubical array pattern, so we will be so the volume of voids is more, and we will be achieving the loosest state. Whereas in the diagonal packing, the volume of voids is less, and we will be achieving densest state. So in the loosest state, the volume of voids will be more, so the void ratio will be more. So general formula of void ratio is the volume of voids to the volume of solids. The volume of voids is more, so then it will be having the maximum void ratio. So in the loosest state, the void ratio will be maximum. So as far as this standard size, spherical shaped, and with respect to cubical array pattern, so the void ratio would be 0.91. Whereas with respect to the densest state, with respect to this diagonal packing, so the volume of voids is less. So here the E minimum, it achieves the minimum void ratio whose value is equal to 0.35. So from here the loosest state would be 0.91, and in the densest state it would be 0.35. Okay, so in a analytical type of question, if they are asking, if they are speaking about some soil whose size is spherical shaped, in that case they won't mention the corresponding void ratio. So in those cases, we want to directly use the 0.91 or 0.35 based upon the type of packing, if they have mentioned, or based upon the state at which the soil is available, whether it is in the loosest or whether it is in the densest state. Okay, so be careful and remember these values. These are very important. Okay, so moving to the next question. The saturated sand sample has a dry unit weight of 18 kilonewton per meter cube. So the dry unit weight of the soil is 18 kilonewton per meter cube, whose specific gravity is equal to 2.65. The unit weight of water is equal to 10 kilonewton per meter cube. So you are supposed to find out what is the water content of the soil. What is the water content of the soil? Okay. So gamma. So the water content of the soil can be calculated from our basic relation E is equal to W into G by SR. E is equal to W into G by SR. So W is equal to E into SR divided by G. E into SR divided by G. So in the question itself, they have mentioned it is a saturated soil sample. So SR equal to 1. So W is equal to E divided by G. So G is directly given. So we want to find out E. So instead of giving E, they have given the gamma D. Using our basic relationship, gamma D is equal to gamma W into G divided by 1 plus E. So gamma W is equal to 10. G is equal to 2.65. 1 plus E. Whereas gamma D is given as 18. So by solving this, we'll be getting an E value of 0.47. By substituting here, E is equal to 0.47 divided by G is equal to 2.65. We'll be getting W is equal to, we'll be getting W equal to 0.47 divided by 2.65 is equal to 17.73, 0.17 or 17.73 percentage. They were asking as in a percentage, so it is equal to 17.73. Okay. Moving to the next question. The Atterberg limits of a clay are given as a 38%, 27% and a 24%. Okay. The water content, natural water content is given as a 30%. The natural water content is given as a 30%. This clay is in which state? Okay. So this Atterberg limits states that it's a boundary water content of the soil. Okay. So as the soil possesses four different states, such as solid state, nothing but solid state, solid phase, semi-solid. So then it also possesses plastic and also possesses liquid state. Different states of soil: solid state, semi-solid state, plastic state and the liquid state. The boundary water content at which the soil changes from semi-solid to solid or solid to semi-solid would be the shrinkage limit. So the limit, nothing but the water content, right, is the shrinkage limit. The water content at which the soil changes from plastic to semi-solid or a semi-solid to plastic would be the plastic limit. The water content at which the soil changes from plastic to liquid state or liquid to plastic state would be the liquid limit. Okay, so as stated here, so the more water content, the highest water content would be the liquid limit. Okay, so this would be 38% and plastic limit, let it be 27, and the shrinkage limit, let it be 24.5. So shrinkage, plastic, liquid. So the water content, natural water content of the soil is at 30%. So the soil is in which state? The soil is in a plastic state. The soil is in plastic state. Okay, moving down. The void ratio of the soil sample is 1. The corresponding porosity of the sample is dash. Okay. So the void ratio is given as 1 and we are supposed to find out the porosity. So the general formula of porosity is the volume of voids divided by total volume. So let me generate a relation. So the total volume of the soil can be written as sum of volume of voids and the volume of solids. So divide the numerator and denominator with volume of solids. So porosity is equal to volume of voids by volume of solids divided by volume of voids by volume of solids plus volume of solids by volume of solids, which is equal to E divided by 1 plus E, which is equal to N. So N is equal to 1 divided by 1 plus 1. So 1 divided by 2, N is equal to 0.5. Okay, the consistency of a saturated cohesive soil is affected by the consistency of a saturated cohesive soil is affected by water content. The consistency is nothing but resistance against deformation, nothing but the resistance of the given soil against deformation. Okay, which indirectly measures the strength. Okay, which indirectly measures the strength. See, with respect to the cohesive soil, this density index does not possess any significance. This density index is provided. Okay, so it provides the compactness of a cohesionless soil. Okay, whereas this particle size distribution, so it is not going to influence in the fine grained soil. Okay, as the cohesive soils are a fine grained soil, The particle size distribution is not going to influence it. So coming to the coefficient of permeability, is a completely different task. So its ability, the ability of the soil, so which allows the water to pass through it. Okay, nothing but a permeability. Okay, so it doesn't possess anything with respect to the resistance against deformation. Okay, so only water content alone changes the strength of the soil, nothing but changes the strength. The consistency of a saturated coagulous soil is affected by water content alone. The void ratio of soil can exceed unity. See, E is equal to volume of voids by volume of solids. So coming to the phase diagram of the soil. So let it be a phase diagram of the soil. So this as volume of solids and this as volume of voids. In total, it is called as a total volume of the soil V. So the void ratio is the ratio between volume of voids and volume of solids, right? Okay. So these two are independent factor, are an independent factor. So one is not a subset or a set of other. As like a porosity, it is the volume of voids to the total volume. So here you can see the numerator is a subset of the denominator. So in this case, what happened? The n value cannot be more than 1. N value cannot be more than 1. So whereas here, the volume of voids and volume of solids are something different. Okay, these two will be varying continuously with respect to the compactness of the soil. Okay, sometime the volume of voids may be greater than volume of solids. Sometimes volume of void may be equal to volume of solid. Sometimes volume of void may be less than volume of solid. So in this case, okay, E will be having any value apart from 0. Apart from 0. Why it doesn't possess 0 in the sense, if numerator, it will get is equal, sorry, the void ratio will get the value of 0 only if the numerator tends to 0. So here the numerator cannot be 0 because my soil, the definition, basic definition of my soil is a unconsolidated particulate matter. Unconsolidated particulate matter in such a way that whatever the pressure I am applying, I can't able to remove the entire voids available in the solid, in the soil. Okay, so in such, with respect to this definition, so E can be any value greater than 0. So the void ratio of the soil can exceed unity is a true fact. So which one of the following relation, is not a correct one? Okay, fine. So let's start with the, okay, there is a basic relation, right? E is equal to W, E equal to W into G by SR. This is a correct statement. Okay, this is a, so let it be. So this is a correct statement. So gamma sat is equal to G plus E divided by 1 plus E into gamma W. The basic relation is gamma sat equal to gamma W into G plus E divided by 1 plus E. G plus E divided by 1 plus E. So this relation satisfies. This relation satisfies. This is also right. So then there is an error with respect to this relation between the porosity and void ratio. So as we discussed, porosity is equal to volume of voids by total volume. So which can be modified as volume of voids by volume of voids plus volume of solids. Dividing the numerator and the denominator with respect to the volume of solids, you will be getting N is equal to E divided by E plus 1. This is the basic relation. So this can be modified in such a way, N into E plus N is equal to E. So by modifying this, N is equal to E into 1 minus N. So from here, E is equal to N divided by 1 minus N. E is equal to N divided by 1 minus N. So statement A also satisfies, but there is a problem with respect to the relation given in the option C. E divided by 1 minus E, it's not so. N is equal to E divided by E plus 1. So option C will be the right answer. Okay, which is not a proper relation or a correct relation. Okay, so consistency index for a clay soil is a liquid limit, LL liquid limit, PL is a plastic limit, PI is a publicity, it's not a publicity index, it is a plasticity index. Okay, so W is a natural water content. Okay, so what is consistency index, right? So consistency index IC is equal to liquid limit minus natural water content divided by the plasticity index. Plasticity index. So I can just modify it as liquid limit, which was denoted as LL, right? Liquid limit minus natural water content divided by plasticity index. What would be the option? The option would be A. Okay, so it was derived from this graph. So volume, so it's a graph. So it's between volume of the soil and water content. Volume of the soil and water content. Shrinkage limit, plastic limit, and liquid limit. The natural water content, let me assume here, and let me define it in such a way that liquid limit minus natural water content divided by liquid limit minus plastic limit into 100 would be the consistency index. Okay, similarly, liquidity index is equal to W minus WL divided by WL minus WP into 100. The sum of these values is equal to 1. So some important relation with respect to the consistency index and the liquidity index.